The motivation behind this project is to provide a visual representation for music for both aesthetic and inclusion purposes. As musicians, our entire team has been interested in this concept for our own practice and performance. Rather than solely using pre-recorded designs, live performers can display the graphic content as part of their performance, which offers flexibility for on-set improvisations. This project is unique because it provides a specialized performance that is inclusive for hearing impaired individuals. Overall, this project adds a depth to music and extends the platform in which musicians can share their art. The initial problem is that music in general is an auditory experience. We desired to create a system that was auditorily as well as visually immersive. Our goals for this project are to collect an electrical signal from an instrument, remove the undesired noise, and develop multiple designs on an LED panel through the use of an Arduino Mega 2560 R3. This includes having to take into account the different power needs for the system subparts. It also requires a software system to be compiled onto the Arduino that will complete a fast Fourier transform frequency analysis and use the amplitude and frequency information gathered to create a color and shape design to then be sent to an LED display. Our hardware specifications of the system include costing less than $300, removing noise below 83 Hz and above 10 kHz through high and low pass filters, shifting the signal to range between 0 and 5 volts for Arduino application, powering all subsystems at reasonable wattages, and lastly, creating a dynamic output on a 32 by 32 LED hardware display. The software specifications of the system include the use of the RGB matrix panel.h library, development of design controller functions, desired fast Fourier transform functions specific to design schemes, global arrays for frequencies and amplitudes, and lastly, shape design drawing functions. Some of the constraints of the project include the size of the LED board limiting dynamic designs, the limiting color options for different notes due to the RGB, clean signal interpretation from an auxiliary input, and lastly, time delay when gathering live data.
The guitar sound is provided by a physical guitar that is connected to the circuit from a 1/4-inch cable to a breadboard-friendly stereo headphone jack. This is the central input for the overall design, and multiple guitars of ranging types can be utilized. An amplifier is needed to ensure a secure input voltage range, but this provides users the ability to further personalize their designs by changing the characteristics of their input signal.
After the guitar sound has been produced, its signal then goes through a high-pass filter. This high-pass filter is desired to have a -3 dB frequency of 80 Hz and 10 dB worth of attenuation at 60 Hz. In order to obtain a filter with a desirable response at low frequencies, an active high-pass filter is chosen. A Butterworth filter is utilized to prevent frequency distortion in the passband. The main strength of this subsystem is its capability to cut off 60 Hz while passing 83 Hz. Due to it being a 7th-order active filter, such a steep slope is permissible. If this circuit were to be of lesser order or a passive filter, the desired response would not be obtained. The main weakness of this subsystem is due to the use of standard capacitances and resistances. Initially, the high-pass filter is designed to have very specific values, but due to only standard resistors and capacitors being available, there is variance in design versus implementation. This can lead to a decrease in performance. After the signal goes through the high-pass filter, it then goes through a low-pass filter. An active low-pass filter is designed to eliminate extremely high-frequency noise. Since a sharp cutoff is not needed, a second-order Butterworth filter is chosen. The strength of the system is its generality. There is no steep cutoff required, and 10 kHz is chosen arbitrarily as the -3 dB frequency to reduce high-frequency noise. In addition, there are only 2 components affected by the use of standard capacitors and resistors, and there is only 1 op-amp in this circuit. Therefore, the weaknesses of the low-pass filter are less prominent than the weaknesses of the high-pass filter. The input signal to the circuit is a sinusoidal waveform. However, the Arduino's analog input can only handle values from 0 volts to 5 volts. As a result, it is decided that the input signal must be shifted up by approximately 2.5 volts in order for it to always be in the desired range. The non-inverting semi-amplifier is chosen to accomplish this goal. The non-inverting semi-amplifier circuit operates as expected. The main weakness in this design is the precision of the resistors used in each voltage divider. Each resistor needs to be a precise value to ensure each signal is being shifted to be centered at 2.5 volts. To combat this issue, 2% tolerant resistors were used. Each op-amp in the final design requires rail voltages of plus 5 volts and minus 5 volts. Since the DC power supply produces one voltage, a circuit is needed to allow for a split supply. In addition to the series resistor combination, two large capacitors are placed in parallel with each resistor. This is done to limit the noise created by the resistors. While this circuit successfully accomplishes the goal of creating the supply voltages for op-amps, it should be realized that its performance degrades if it experiences loading effects. Since the op-amps used in the circuit reduce loading effects to around 2 milliamps, this does not cause a large problem.
The Arduino Mega 2560 is the backbone for all software-related intricacies within the project. It is also the central communication port between all major subsystems. The preprocessed signal and design buttons serve as input to the Arduino, and all driving data is outputted to the LED matrix. In regards to the software implemented on the Arduino, it processes the input signal for design creation. Processing includes running the preprocessed signal through one of two fast Fourier transforms. Both transform functions calculate the frequencies existing within the signal, but one calculates the dominant frequency while the other categorizes the frequencies into 32 defined ranges. The former transform is used to determine the dominant note played within the input signal. This is crucial for designs that showcase the note, pitch, and amplitude currently being played. The later transform is used for the frequency analysis designs. The LED matrix is 32 by 32 pixels, so 32 ranges are used to showcase the existence of various frequencies. The sampling rate for the software does slightly vary due to the collection method, but it does not negatively impact performance due to the function's categorization. The software is also modular and requires no alteration from the user to run appropriately. The design push button connects to the Arduino Mega 2560 as a medium for users to select the preferred design option. Users are able to cycle through the available designs by pressing the push button rather than through software interaction. The button is controlled with a software-based bouncer, so there is an occasional bounce when the button is pressed. The LED matrix is the central output for the overall design. It receives input from the Arduino Mega 2560 and enables the internal LEDs accordingly. Collectively, the enabled LEDs display the design created from the input signal. The matrix is powered to the highest degree, so the LEDs are exceptionally bright, which can make one of the designs problematic for users sensitive to light. This also causes some pixels to partially light up when the design does not specifically call for them to drive down.
The performance of the pre-processing subcircuits can be analyzed by running experimental signals through each subcircuit and showing how the signal is manipulated in the output. The figures shown on the screen are FFTs of the output corresponding to an input test signal. As can be seen, signals below 80 Hz and above 10 kHz are diminished, while all others are preserved. To test the processing circuit, including the non-inverting semi-amplifier, a similar process was performed. On the right side of each figure, the values for the input, shown in yellow, and the values of the outputs, shown in blue, express that the circuit implemented shifts the signal to oscillate at a mean of 2.48 volts. It is important to note that in this figure, it can be seen that the 60 Hz hum is removed from the signal.
In theory, each note and pitch has an average frequency that can be defined. Originally, the note and pitch classification ranges were centered around the theoretical averages. In physical practice, these ranges slightly deviated from the expected results, so experimental testing was used to tune the ranges for physical performance. This table showcases the final ranges for note and pitch classification. In regards to the fast Fourier transforms, the sampling rate is 5,378 samples per second. The bin width varies based on the design implementation. For frequency analysis designs, the bin width is approximately 28.375 Hz. However, note and pitch detection designs have a varied bin width based on the particular note and pitch.